Imagine shining light through a transparent material. You expect it to pass through, slow down a bit, maybe bend. That's what the refractive index tells us. But in some special materials, light hits an invisible wall. Imagine shining light through a transparent material. You expect it to pass through, slow down a bit, maybe bend. That's what the refractive index tells us. But in some special materials, light hits an invisible wall. Certain colors simply cannot pass, no matter how thin or transparent the structure appears. This is the photonic band gap paradox. It reveals how engineered materials like photonic crystals can block specific light frequencies altogether, not by absorbing them, but by using structure alone. That means even if a material's refractive index suggests it should be transparent, light at some wavelengths just gets stuck. In this video, we uncover how these paradoxical materials work, not by changing what they're made of, but by how they're arranged. Much like how electrons face barriers in semiconductors, photons encounter forbidden zones in periodic structures. These photonic band gaps arise from wave interference, not classical optics. So the behavior of light in these materials depends less on what the material is and more on how it's built. This flips our everyday assumptions and unlocks the design of advanced technologies, like ultra-efficient LEDs, invisible cloaks, and precise optical filters. What seems like a simple trick of light is actually a deep insight into how geometry and wave behavior combine to reshape our control over light itself. This flips our everyday assumptions and unlocks the design of advanced technologies, like ultra-efficient LEDs, invisible cloaks, and precise optical filters. What seems like a simple trick of light is actually a deep insight into how geometry and wave behavior combine to reshape our control over light itself.
Photonic band gap paradox. How can engineered materials selectively block specific light frequencies while allowing others to pass, seemingly challenging the traditional predictions based solely on refractive index models, even though the behavior of light is governed by well-established electromagnetic laws? In conventional optics, materials are characterized by their refractive indices, parameters that predict how light bends, reflects, and propagates through them. Classical models suggest that if one knows the refractive index of a material, it should be possible to forecast the transmission and reflection properties for a continuum of light frequencies. In an ideal world, these predictions would be straightforward and largely independent of complex interference effects. Yet, in practice, engineered photonic crystals and other periodic dielectric structures have demonstrated a remarkable ability. They can selectively prohibit the propagation of light within specific frequency ranges known as photonic band gaps, while allowing other frequencies to pass unimpeded. This counterintuitive behavior forms the core of the photonic band gap paradox. So far, so good until we delve into the intricacies of light-matter interaction in these structured media. The photonic band gap paradox arises when the simplicity of traditional refractive index models collides with the complex collective behavior of light interacting with a periodic structure. Under idealized conditions, where a material is treated as a continuous medium defined solely by its bulk refractive index, one would expect a uniform behavior across the light spectrum. However, engineered materials like photonic crystals are designed with periodic variations in refractive index on the scale of the light's wavelength. These variations create interference patterns that give rise to band gaps, frequency ranges in which electromagnetic waves cannot propagate. One striking example occurs in 2 or 3-dimensional photonic crystals. Here, the periodic arrangement of high and low index materials leads to multiple scattering events and constructive or destructive interferences. Much like electrons in a semiconductor encountering periodic potential wells that result in electronic band gaps, photons in these structures are subject to a similar filtering effect. Despite the underlying electromagnetic laws being perfectly reversible and well understood, these systems exhibit a behavior where certain frequencies are fundamentally excluded from propagating, in stark contrast to what one might anticipate from an analysis that considers only the average refractive index. At even smaller scales, the picture becomes even more intriguing. In a photonic crystal, the spatial periodicity introduces a kind of meta-refractive index that is not captured by simple, homogeneous models. Instead, the wave nature of light interacts with the periodic lattice to form complex standing wave patterns. The number of allowable photonic states is drastically reduced within the band gap, and the system's response is dominated by the structural geometry rather than solely by material composition. This means that even if individual layers or components have refractive indices that would suggest transparency, their collective arrangement can result in an effective barrier to certain light frequencies. And then there is the matter of structural imperfections and environmental factors. In real-world applications, slight deviations from perfect periodicity or variations in fabrication can alter the boundaries of the photonic band gap. These perturbations can either slightly narrow or broaden the range of frequencies that are blocked, much like how minor fluctuations in a turbulent fluid can tip the balance from laminar flow to chaos. These subtle alterations in the crystal structure underscore that the observed band gap is a result of collective statistical behavior rather than the simple local properties of the material. So, what is truly happening? The paradox does not undermine the basic laws of electromagnetism. Instead, it highlights the limitations of relying solely on traditional refractive index models for predicting the optical behavior of complex structured materials. The concept of a photonic band gap emerges from models that fully account for the wave interference effects, geometric symmetries, and the collective scattering behavior within a periodic medium. In essence, while the microscopic Maxwell's equations remain fully reversible and deterministic, the macroscopic behavior of light in these engineered materials is dominated by emergent properties that bypass our naive expectations. The photonic band gap paradox serves as a powerful reminder that our understanding of light-matter interactions must extend beyond simple scalar refractive indices. It challenges us to consider the profound effects of periodicity, interference, and structural design, a perspective that not only refines our theoretical models, but also drives innovative applications such as optical filters, waveguides, and efficient light-emitting devices. This richer, more nuanced understanding illustrates how engineered materials can harness the collective behavior of light to achieve outcomes that defy conventional wisdom, opening up exciting avenues in the field of photonics. The photonic band gap paradox reveals that engineered materials can selectively block specific light frequencies despite conventional refractive index models. These materials achieve such selective filtering by relying on their internal periodic structure rather than their homogeneous bulk properties. This phenomenon challenges the traditional view that light propagation is dictated solely by a material's uniform refractive index. A photonic crystal can be designed to reflect near-infrared light while allowing visible light to pass through. It is like a custom-built sieve that lets only certain sized grains fall through while blocking others, despite having the same overall composition. Classical optical models assume that light interacts uniformly with matter based on a constant refractive index. Photonic band structures, however, arise from periodic variations in a material's dielectric constant that create interference effects. This distinction underscores how spatial periodicity leads to unique frequency ranges where light propagation is forbidden. Unlike homogeneous glass, a photonic crystal with a periodic lattice can completely block a narrow band of light frequency. It is like comparing a plain window that transmits all light to a patterned filter that selectively dims certain colors. At the microscopic level, the periodic arrangement of materials in photonic crystals causes light waves to interfere with one another. Constructive interference enhances transmission at allowed frequencies, while destructive interference prevents the propagation of specific wavelengths. This interplay of interference effects is the key to the emergence of photonic band gaps. In a one-dimensional photonic crystal, alternating layers create interference patterns that block certain wavelengths entirely. It is like a chorus singing in synchrony for some notes, while canceling out others, resulting in a selective acoustic effect. The creation of a photonic band gap is governed by the periodic modulation of the material's dielectric properties, which alters the optical modes available for light propagation. This modulation causes light waves at specific frequencies to encounter repeated phase shifts, resulting in the cancellation of those waves. The effect, therefore, is not due to material absorption, but to engineered interference within the structure. Silicon photonic crystals use nanoscale patterning to generate band gaps that can stop certain wavelengths of light used in optical communications. It is like arranging mirrors in a room to systematically cancel out echoes at particular pitches rather than absorbing the sound energy. While perfect periodicity creates well-defined photonic band gaps, introducing structural defects can localize light within the forbidden frequency ranges. These controlled imperfections allow for the guidance and confinement of specific wavelengths that would otherwise be blocked. Consequently, defects add tunability and additional functionality to the photonic crystal. Deliberate defects in photonic crystals are used to create high-quality optical resonators that trap light for extended periods. It is like a small gap in a fortress wall that, instead of weakening the defense, acts as a controlled gateway to manage the flow of people. The periodic structure of photonic crystals governs not only the blocking of light, but also its diffraction and the paths available for transmission. As light traverses these microstructured materials, the diffraction patterns determine which frequencies are allowed and which are suppressed. This selective information flow differentiates photonic crystals from conventional optical materials that rely solely on refractive effects. In three-dimensional photonic crystals, complex diffraction phenomenon can lead to complete band gaps where light is blocked in all directions for certain wavelengths. It is like a well-designed labyrinth that channels movement along specific routes while completely isolating other pathways. Photonic band gap materials have significant implications in advancing optical technologies such as lasers, sensors, and optical computing. Their ability to control and manipulate light with precision leads to more efficient and miniaturized devices. The phenomenon also provides insights that push the limits of conventional material science and optical engineering. Photonic crystals are being integrated into optical circuits to create all optical switches and low-threshold lasers. It is like upgrading from a broad highway to a network of finely tuned express lanes that direct traffic with exceptional precision. Designing photonic crystals requires nanometer-scale precision in fabrication, which poses significant technical and material challenges. Accurate modeling of the interference patterns and defects is essential to predict the exact band gap behavior. Yet even minor imperfections can lead to unpredictable outcomes. The complexity of these materials demands advanced fabrication techniques and rigorous quality control. Achieving uniformity over large areas in silicon photonic crystals remains a major hurdle in scaling up production for commercial optical devices. It is like constructing an intricate mosaic where every tiny tile must be perfectly aligned, as even the smallest misplacement disrupts the overall pattern. Future research will focus on integrating photonic band gap materials into a wider array of optical and electronic systems, expanding their applications and performance. Advances in nanofabrication and computational modeling will enable more precise control over light propagation and further innovations in optical device design. These developments promise to revolutionize fields ranging from telecommunications to quantum computing, by harnessing the unique properties of engineered photonic structures. Researchers are exploring reconfigurable photonic crystals that can dynamically alter their band gaps in response to external stimuli for adaptive optical systems. It is like transitioning from a static map to an interactive real-time navigation system that adapts to changing conditions, providing smarter and more efficient guidance.